So this works and it's good, but whenever you see some code that looks like this, that has a bunch of nested if, else if, else if, else if, it's kind of a hint that maybe there's a more elegant way of doing this. And as you begin to learn more and become more and more programmers in your studies, you'll find that things like this are danger signs, that perhaps there's a more elegant way of solving a solution. As you can imagine, this isn't very easy to maintain if you want to add additional bases to look at, or there are, you find an error, you have to go through each of your elif statements to find out what's going on. So while this works, there's got to be a better way of doing it. And the better way involves dictionaries that we introduced before. So we're going to tweak our code. I actually saved it as a new version, revcompdictionary.py. But the aim of this is to achieve the same thing, but in a more elegant way using a dictionary. Okay, so the first part of the code looks the same. We still import sys, still have my code comment, I'm still defining a function, and I'm still starting with an empty string called rcseek that is empty, ready to be filled with values. The next thing I have is a dictionary. Remember, you can tell it's a dictionary because it starts with these curly braces and everything is separated by, each key and value pair is separated by a comma, and each key and value is separated by a colon. So I have this complement dictionary where every key has a value that is the complement nucleotide. So the key A has the value T, the key T has the value A, the key C has the value G, etc. So we have a dictionary where every nucleotide has its value associated with it in the dictionary. That is, so the key has the complement as the value. Okay, so now that we have this complement dictionary where we can look up the complement nucleotide, we can make use of that, and rather than having if, elif, elif, elif for every different combination, we can just look up in the dictionary the complement nucleotide. So now the processing is the same for every nucleotide. So for nuc in seq, I'm first going to check if my nuc is not in AGCT and print that it isn't, so this bit stays the same. But previously in the else statement we had if and elif a bunch of times here. Now we simply have else rcseek equals the value in the complement dictionary associated with the key nuc prepended onto the rcseek. So compare that to what we had before, where we had if, elif, elif, and we were prepending each letter. We're still doing the same thing. We're still prepending the letter onto the beginning of the sequence. The only difference is, rather than having to check what each letter is, we're always going to prepend the value in the complement dictionary associated with the key nuc. So if nuc is A, it's going to go to the complement dictionary, look up the value associated with the key A, it's going to find that the value is T, and it's going to prepend T onto the beginning of our complement dictionary. And so that's it. We have changed the if and elif, elif, elif pile of code into a single line where we do the same thing for every nucleotide. We just put the value associated with it in the dictionary at the beginning of our output string. So when you've made that change, the rest of the code is the same. Let's save it and run it. You can run the old version and the new version, and as I show here, they should both produce the same results. I'm not necessarily saying that the one with the dictionary is going to run any faster. You know, this runs so fast that we wouldn't be able to tell. If you worked with a larger sequence, you might be able to see performance differences. But the main reason for doing this is for clear, concise code and for maintainability. You know, if you want to change the way this code works, if you want to add some degenerate bases or whatever you want to do, it's much easier when you have this complement dictionary where you can make changes. So just to recap, what this does is it goes through for every nucleotide in our input sequence. It checks whether it's in AGCT. If it is in AGCT, it's going to look up the value associated with the key in the complement dictionary and prepend that onto the output sequence. So if it goes through for this sequence, it will find an A. It will look up the key A and find the value T and prepend that onto the output sequence. It will then go to the next one, which is G, look up G, find the value C, and prepend a C onto our output sequence. So it goes through letter by letter, looking up the value associated with the key in the complement dictionary. Everyone with me?
What is the return and empty
Yeah.
thing?
Why what, sorry?
We do not have the return and empty thing.
Yeah, you don't need that.
Okay.
So that's just say if you put an X in your sequence and you wanted it to stop and tell you that it was an invalid nucleotide and not bother interpreting the rest of the code, then you would have that return statement in there. If, however, you wanted it to keep going, ignore the X and keep going, then you can get rid of the return statement and it will keep going. So it depends whether you want it to stop and alert you or whether you want it to keep trying. Awesome, okay. So I just need to introduce a couple more data structures that aren't widely used, but you might see, especially if you pick up other people's code and need to extend perhaps code that exists within your lab already. The enumerate function is a great way of adding indexes to lists. So it's a great way of pairing numbers with values in a list, for example. So if I have a list of seasons, which might be spring, summer, fall, and winter, I can run enumerate on that list. And what it will do is it will pair 0 with spring, 1 with summer, 2 with fall, and 3 with winter. And then I can look at that by casting it to a list. Remember that we can cast things to a float, we can cast things to a string. We've seen lots of casting to floats. You can even cast things to lists. The reason we do this is actually a Python version thing. With Python version 2, you can run enumerate seasons and you might see the correct result returned. But with other versions of Python, you need to convert it to a list to be able to see the correct results. If you run list on something that's already a list, it's not going to cause any problems. So if in doubt, you can always cast things to the data type they already are, and it's fine just to check. So once I've run enumerate on my list, what I can do is I can do a for loop over that output and print each one in turn to see the results. So I see that 0 is paired with spring, 1 is paired with summer. I wouldn't worry too much about enumerate. It's not something I use too often, but just so you're aware that it pairs every element in the list with another index, which is useful if you're then going to put it in a dictionary and lose the order, or you want to output it to a file and have 0 in one column and then the first thing, 1 in the next column and then the next thing. If you want to number your outputs, it can be useful. So the other useful thing is zip, and that zips together two lists. So if I want to zip together the list 1, 2, 3 with the list A, B, C, I run zip and I put both those lists in brackets separated by a comma, and the output is going to be the two lists zip together such that the first element of the first list is paired with the first element of the second list. And so what we get is 1A, 2B, 3C. And then again, if you want to see what's going on, you can do a for loop over that zipped list. So here I do for x and y in my zipped list, let's print x multiplied by y. Now, previously when we've seen for loops, we've always seen one variable here. We've seen for nuke in sequence, or for letter in name, for letter in Python, or whatever it was. You can, if you're iterating over something that has multiple elements like this, so you see that the zipped list has a 1 paired with an A and a 2 paired with a B, you can actually put multiple variables here and it will iterate over them both together. So for x and y in zipped list, it's going to set x equal to 1 and y equal to A the first time. I'm then going to print x multiplied by y, and what that will do is A multiplied by 1, which will repeat A once, and we should see A printed to the screen. The next time it's going to set x equal to 2 and y equal to b. I can then do print x multiplied by y. And what I will see is 2 multiplied by b, which is b twice. So I get b printed twice to the screen. 3c will print c 3 times. So it will go through printing each one of those elements the number of times specified in the first list. This is a pretty trivial example, but the zipped list is useful if you want to, often you have a big list of gene expression values and a big list of gene names, and you want to pair them all up before you output them. So you want to make sure that your expression level with the first gene is paired with the expression level that you recorded, and so you might zip your list of outputs with your list of identifiers using zip. Any questions about that? Okay, so something else that catches people out is break statements. What they do is they stop the code executing an exit out of the loop they are in. So if the code is going through a loop, for example a for loop, and it hits a break statement, it will stop looping through the data. So the reason this catches people out is because they might see a bit of code that looks like it's going to do something for every gene in an input sequence, and when they run the code they only see the first 10 genes shown on the screen, and they can't figure out why, and it's because somewhere in the code there's a break statement hiding that has broke the execution of the for loop. So here's an example of what I mean. What I have done is written a square root function, so def square root of n, which is going to take a list of inputs, a list of numbers. This n is not a single number, it's going to be a list of numbers. And then it's going to, for every number in that list, do something. And what it's going to do is it's going to check if the number is less than 0, and if it is, it's going to print that it can't take the root of a negative number and break. So it will finish executing the for loop and not try and take the square root of this negative number because it hit the break statement. So the alternative way of doing this is saying if the num is less than 0, print that you can't take the root of a negative number, else take the square root of the number. That's probably the more elegant way of doing it and the way that I would do it, but you often find people use break statements like this because it just makes the code a little bit smaller. And if you notice, there is no else statement. The square root code is in line with the if, so it will happen every time. The only reason this code doesn't try to take the square root of the negative numbers is because it will first reach a break statement and stop going through the list. So if we have a list with a negative number, it will get that far, it will check, it will find the number is less than 0, it will print that it can't take the square root, and then it will break. So it won't then run this line because of the break statement.
So you use one break when, like when you know that from certain point, this is not going to work. Like
Right. Either from a certain point it's not going to work, or from a certain point you found what you're looking for. If you're going through a big, the whole genome, and you're looking for a sequence and you found it, you might want to break. So it's a good way of stopping a loop. They can be tricky, and sometimes there are better ways. But yeah, if you want to stop something looping that's going through a lot because you know you're done or you know it won't work for whatever's coming next, you can use the break statement. Okay. What do you say, sir? Can you use reader? Return? Instead of break. You could use return. You could, rather than breaking, return nothing, and that would have the same effect. But if you don't want to finish executing your entire function, you just want to stop the for loop and then do whatever's after it, that's when you would use break. So for this example, there's nothing after the for loop. So we could have used return and just stop executing the function. But you might have a function that goes through a for loop looking for your sequence in the genome. When it finds it, breaks, and then does something with that sequence. And if you had a return statement, you would never get to whatever comes next. So break will exit the for loop without exiting the entire function. That's why you would use break rather than return. The break will take you out of the for loop, not the if statement. It'll take you out of whatever loop you are in. An if statement isn't a loop. So the break statement will take you out of the loop you're in without taking you out of the function you're in. So the return will take you out of the full function and finish executing the entire function, whereas the break will stop the for loop. Does that make sense?